Today I'll be speaking about a paper by Jeremy Butterfield titled Peaceful Coexistence, examining Kant's relativistic solution to the quantum measurement problem. Now, the reason why I'm interested in this is because I'm doing a doctorate in philosophy and I'm interested in the philosophy of Aristotle, and I think Kant's account of the measurement problem is in some way amenable to an Aristotelian interpretation of reality. So in Aristotle, things are ordered towards some end, and there's something about Kant's theory which I think is amenable to such an interpretation. However, I think as far as I know, Kant has no interest in Aristotle, and he might think that I'm completely butchering his account of the measurement problem by trying to look for sort of an Aristotelian spin on what he says. But in this talk, I'm not really going to talk about my own philosophical interests with Aristotle, because I think Kant's relativistic solution to the measurement problem has great merits just in its own terms, regardless of what other kind of ontological assumptions you might want to impose upon what Kant says. So first, give you an outline. So first, I'll examine the possible conflict between special relativity and quantum theory. And so the source of this conflict is the experimental violation of Bell's inequality. Then I will consider Shimney's proposal for peaceful coexistence via the distinction between outcome independence and parameter independence. Then I will look at Butterfield's critique of Shimney's proposal. Then I'll consider Butterfield's appraisal of Kant's proposal to the relativistic solution to the quantum measurement problem. And so Butterfield thinks Kant's proposal fares much better than Shimney's. But I also have to look at the consistency of Kant's theory with quantum theory and the consistency of Kant's theory with special relativity. So let's look at the possible conflict between special relativity and quantum theory. So it seems that they might be at war, and the source of this conflict is Bell's inequality theorem. So if you need a reminder of what this says, so really what you consider is a spin singlet, that two particles in opposite spin states as in they're superimposed on one another, and one particle is sent to Alice and another particle is sent to Bob. So if they make the measurement in the same axis, they always measure opposite results. So if you change to the spin x-axis, they'll always get the opposite results. Now this might be a worry from a special relativity point of view because it seems to violate locality. So one way to address this problem would be just to say, well, we have hidden variables. So here you have these variables for particle 1, these variables for particle 2, and you notice here you have the variables for particle 1 and the variables for particle 2, and you see that they have opposite signs. And so this might be a way of preserving locality because all the information is encoded locally in the particle. However, what Bell showed is that if you have such hidden variables, then you have to have this inequality being satisfied. On the other hand, quantum mechanics indicates that the probability should look like this, where theta AB is the angle between Alice's measurement and Bob's measurement. And so if you plug in a value of theta AB equal to 2 theta and theta AC equal to theta CB and take theta to be pi by 4, then we get 0.5 is less than 0.292. That's if Bell's inequality really held. And you may think that quantum theory is weird, but it's not that weird, that we can't have a hidden variable theorem, hidden variables according to Bell's inequality. This is what it seems to show. However, Shimney, he proposed that, well, maybe things aren't quite as hopeless as Bell makes it appear. So he thought that we could identify the culprit. So Shimney, he asked, does Bell make a locality assumption that can be violated without violating special relativity? And Shimney said, yes, he did. And so to consider Shimney's analysis, he considers the quantification over these terms where lambda is the physical state variable, x and y are measurement settings, and capital X and Y are measurement outcomes. And Shimney says that Bell makes the following assumption, that the outcomes X and Y are statistically independent. However, in this equality, Bell makes two implicit assumptions, outcome independence and parameter independence, which I'll explain shortly. But the point is, Shimney claimed that you could have a violation of outcome independence but still be compatible with special relativity, whereas violations of parameter independence would not be compatible with special relativity. And so the actual meaning of parameter independence is that we call your physical state, and this is the actual measurement that is made, and this is measurement outcome. So this is well defined. So regardless of what goes on at the other measurements, we're indicated by y, if you sum these two values, the outcome of y and the outcome of not y, then this is not going to affect this value here. You always get the same result. So this probability is well defined and is independent of the y measurement. And outcome independence is just saying that, assuming that this is well defined value here, then if you just assume that this is going to be statistically independent from this random variable. But in this outcome independence, you don't make any assumptions about parameter independence, so you have to have the y here. So what's Butterfield's concern? Well, Chimney analyzes Bell's theorem in wholly non-relativistic terms. Now, this might seem a little bit strange. If you're kind of trying to show that two things are consistent with one another, you actually might want to actually say something about what you're talking about. But really, Chimney really looks at quantum theory itself rather than having any regard for special relativity. So there doesn't really seem to be any intersection between what Chimney is really saying about special relativity. So that kind of raises concerns. But also, Chimney says that outcomes can't be influenced non-locally. But Chimney doesn't say what he means by outcomes. And so Chimney is really sidestepping the whole measurement problem. So the measurement problem is, if the wave function is something physical rather than something epistemological, what happens to the wave function when a measurement occurs? So what happens compatible with special relativity? So for instance, if you had, say, like a Copenhagen interpretation of measurement, then if Alice is making her measurement and Bob is making his measurement, there's a question about who actually collapses the wave function. Is it Alice or Bob? Because in some inertial frame, Alice makes the measurement first, and in another inertial frame, Bob makes the measurement first. So this seems rather puzzling. Can we really accommodate special relativity and quantum theory together? Butterfield thinks that Kent's proposal is much more promising. So what Kent proposes is that physics plays out between hypersurfaces S0 and S. And then what you do is you take an initial quantum state psi0 defined on S0, and then you unitarily evolve it to the state psi s on the final hypersurface S. And what you do is, given this final state psi s, you also have an operator on it, a Ts, which is depends on the energy momentum tensor, and you just choose one possible mass energy distribution, Ts of x, according to the Born rule. So it's like you make some notional measurement. So it's not supposing that he actually saying that there is some kind of measurement that's made, but it's just a mathematical technique to sort of show how you get your history. This is our fictional measurement that we get, that are highlighted in purple, and then for point y between S0 and S, its energy momentum is given by the expectation value of the energy momentum tensor at y, but importantly, it is conditioned on the mass density being Ts of x outside of the light cone y. So we are conditioning on this information here and this information here, and we throw away this information here when we're working out the energy momentum expectation value here. And something to note about this theory is that it appears to be Lorentz invariant. So the information on which the energy momentum of y is conditioned is Lorentz invariant, because we're using this light cone to tell us which information we have. Kent goes on to consider a toy model for the wave function collapse. So this you can think about really what is happening when a measurement is made. So in this very simple example, Kent supposes that you have two mass locations situated at x1 and x2 with corresponding wave function psi1 and psi2, and he supposes that these two mass locations are in superposition with one another. So you have this superposed wave function psi0, and we appropriately normalize it so that a squared plus b squared equals 1. And Kent supposes that you have a photon that flies in and it interacts with these two mass locations. So initially you're going to have a joint wave function of this expression here. So this direct delta is for the photon, and this superposition is just for the superposition of the masses at x1 and x2. And then you evolve your wave function further, and things are going to get entangled. So when you work out the wave function after this interaction, you see that this minus has turned to a plus, so the photon is now going in the opposite direction. But the other possibility, the photon hasn't yet interacted with system 2, so we're still going in the same direction, so you have the minus sign here. And then as you evolve further, the photon finally interacts with the second system. It's going to be useful to make a note of this distance here to get you down to here. This is going to be a significant point in Kent's account of wave function collapse, and so we can work out the joint wave function now. So now that the photon that interacts with the x2 mass location, that's now going in the opposite direction. So how does Kent use this account to determine what the mass density is at particular points in sort of the world history? So he supposes that the photon actually that the measurement is actually measured to occur on at this point, which would indicate that the photon had interacted at mass location x1. And so for mass density distributed, so for times t less than 2 t1 minus t2, so this is at this point before, so this is the point where the photon interacts with the second mass location. So if you make your work out your mass density at this point, then the mass density is going to be distributed according to psi y squared, with a proportion of a squared localized around the y equals x1 location, and a proportion of b squared localized around the y equals x2 location. So it's a bit confusing with the x here and the y there, but anyway. So, and to see why this is the case, you just say standard quantum. This is really what you get from just standard quantum theory. And so when you see here, when you condition on here, there's actually no information about where the photon interacted with the system, so that you just get exactly what you'd get in standard quantum theory. Again, there's no information here about the particle interaction, so you get a squared proportion here and a b squared proportion here of the total mass. So for times when the t is greater than 2 t1 minus t2 and less than t1, a proportion a squared of the total mass system is going to be distributed around x1, and nothing is going to be distributed around x2. So to see why this is the case, we consider now the light cone. So here, the information here, there's absolutely no additional information beyond standard quantum theory on which to work out the value of the mass density here. So you're just going to get the usual result, so which will be a squared. However, at this point, you see, when the value is calculated beyond this point here, then you're going to have information about where the photon interacted with the hypersurface S. So when you're here, you definitely know that there's going to be no interaction here, so there's going to be nothing here for the photon to interact with, but the photon, you're going to know that the photon is going to interact here. So, but at this point, from this perspective, you know that there's going to be no mass is going to be distributed around x2. There's going to be nothing for it to interact with. And then finally, when t is greater than t1, the full system is going to be distributed around x1 and nothing is going to be distributed around x2. And again, to see this, you just now when you do your conditional expectation on the information here, you see now you know that the photon did interact with the mass located at x1, and so there's nothing that's going to, there's going to be no possibility of any further interactions with the location at x2, and it's just going to be the same. That from here, you know, there's going to be you've got the information there, so we work out on condition of this happening that there is nothing here. So Butterfield goes on to consider the Kentian toy model of a Bell experiment. So rather than considering particles that are spin up and spin down, Butterfield considers a situation where you have an entanglement of matter located at these locations x1 and x2 and x3 and x4. So the wave function is going to be, the joint wave function is going to be this entanglement here, where psi I is localized around xi. Now YL and YR are the spatial coordinates of the left and right systems respectively. And again, we have a squared plus b squared equals 1. And so this really sort of captures or something of the Bell type experiment. And so what you consider is a photon comes from the left and a photon comes from the right. The left photon interacts with the left system and the right photon interacts with the right system. And then a notional measurement is made on S, which registers whether the left photon is reflected from x1 and the right photon is reflected from x4, or whether the left photon is reflected from x2 and the right photon is reflected from x3. So we assume that it's actually case A that occurs. Then at a space-time location on S prime, shortly before the left photon interacts with the left system, the mass density on S outside the light cone determines that the photon will be reflected from x1, because you see we have this information in here. So we know that the photon on the right interacts with the x4 location, so we know that the photon on the left is going to interact with the x1 location. And there's going to be a similar story for the right system. So we see that according to standard quantum mechanics, that when you make this prediction, you're going to predict a proportion of the matter being located at x1 with probability a squared. There's a proportion of a squared of the matter would be located there according to standard quantum mechanics. Whereas in Kent's account, so when it's sufficiently close, you're going to know for certain that with probability 1 that all the mass is located in this left-hand system at x1. So you might worry that you actually get Kent is offering a theory that is distinct from standard quantum theory. I'll try to show you why this in itself is not a worry, but we have to admit that quantum mechanics and Kent's theory give different measurement probabilities. Another thing worth considering is the issue of outcome independence, which was which Shimney considered, where you assume that x and y are statistically independent. Now it's fairly easy to see that any deterministic theory satisfies outcome independence. And furthermore, so given lambda equals Ts, Kent's theory is deterministic. So this means that, unlike quantum mechanics, Kent's theory satisfies outcome independence. But although Kent's theory is distinct from standard quantum theory, this is not necessarily a problem. And because we have this expression here, this is really telling you that experimentally that you wouldn't be able to tell the difference between Kent's theory and standard quantum theory. So here we have the standard quantum mechanical probability. So here we have Kent's probability, and here we have the space of all possible mass density measurement outcomes on S. And this is something that in principle that we can never know. So the best that you can do is that you take the weighted probabilities according to the measure on TS. So given your state psi S, there's going to be a distribution of possible mass densities that you could measure on your final hypersurface. And you calculate these probabilities in terms of the Born rule. And then it seems that Kent's theory is experimentally indistinguishable from standard quantum mechanics. So what about the consistency of Kent's theory with special relativity? So here we ought to again consider parameter independence. So if parameter independence were to fail, then we might worry that this really would be a problem for any account of physical reality. So here is not going to be well defined. So this is a probability that you have outcome X when you have your measurement setting set to X, and this describes your physical state. And if you have parameter dependence, and this is not going to be well defined because someone else might make a measurement at position Y, and what's going to happen is that you're going to get different values here depending on what, say, if this Y is what Bob measures, that Alice is going to work out different probabilities based on what Bob sets his parameters to. So this is so long as Alice knows lambda. So we just consider this briefly in the spin up and spins down singlet state. So they, if they're measuring on the same axis, they'll always get opposite values. But if they measure, on different axes, it looks like if parameter dependence held and Alice knows lambda, then in principle she could work out the measurement Bob performed, and hence Bob could send messages to Alice faster than the speed of light. So this seems to be like a big red flag if you want to maintain special relativity. However, according to Kent's theory, it is completely impossible for Alice to know that lambda equals Ts. So from that point of view, even if parameter independence is violated, it doesn't seem like a complete disaster because there's still no information that Bob could convey to Alice. So they're going to make the following points about whether Kent's theory is consistent with special relativity. So it does appear that Kent's theory is Lorentz invariant. Now Butterfield thinks that it's an open question of whether Kent's theory violates parameter independence, but personally I think that Kent's theory does violate parameter independence as far as I can see, but I can't see why this would violate the spirit of special relativity, given that it's intrinsically impossible for Alice to know what this parameter lambda is. Because this means having to know what the mass density is on this final hypersurface, and this is going to be impossible in this framework. and we kind of assume that Alice doesn't have premonitions of the future. So Butterfield also thinks that Kent needs to address a no-go theorem of Kohlberg and Renner et al. So the no-go theorems are really saying that you can't have everything that you really want for a theory. So this no-go theorem, it supposes that you have this equality here. So this is really just saying that this hidden variable theory is experimentally indistinguishable from standard quantum mechanics. So here we have an observable O hat, and we have an eigenspace projector of O hat, and this probability here is just a standard quantum mechanical probability, this expectation value of the projector E hat, and you have lambda, which is a hidden variable, as I put hidden in quotation marks here because I mean we're not, although TS in Kent's example is intrinsically hidden, you don't necessarily need to commit itself to being a hidden variable, but really it's kind of like a variable that's sort of supplementary to standard quantum physics. And then we have this the space of hidden variables. So e.g. this would be the space of all possible measurement outcomes on your final hypersurface TS. So this is the one of the suppositions of this Kohlberg and Renner theory, but it's really saying is it Lee Water. He's the one actually kind of putting it in this kind of formulation. And also you have mu here is a measure on your hidden variables. So it's just supposing that you have absolutely no knowledge about lambda, then the best that you can do is just take a weighted average of all your probabilities here. And it's assumed in this theorem that the measure on capital lambda is going to be independent on the measurement O hat. And so in this theorem it also assumes that parameter independence holds. And then what if you have these two things, then it means that the hidden variable probability of E hat is going to be the same as the quantum mechanical probability, sort of almost everywhere. And now this just seemed to be problematic insofar as, if you're going to propose a new theory of physical reality, and your physical reality not just in a measurable way, but it gives you exactly the same results from every kind of possible mathematical consideration. It just seems that coming up with your theory is just a complete waste of time. So really what you want for your addition to quantum mechanics is you want something that it does actually give you different results from quantum mechanics on the microscopic level, but when you actually average over all these, you get the same result as quantum mechanics on the averaged level, on the sort of macroscopic level. So that's really what you want from your addition. Otherwise you're not really adding anything significant to quantum mechanics. So this no-go theorem says that you can't have all these things that you really desire. You want to have this, and well, a lot of people are very wedded to the idea of parameter independence if you're going to have special relativity holding, and you want to have this not equal to this because you want your supplementary theory to be saying something new, whereas this suggests that your theory is not saying anything new at all. So it's just becomes this identical really with standard quantum mechanics. One way to overcome this would be, as I'm sort of attracted to, is to say that, well, parameter independence violation is not such a big deal. I mean, of course, in some situations it really would be a big deal. I mean, maybe in the Bohmian interpretation, although the variables are called hidden variables, if it might be that eventually you could find some way of actually just really discovering these hidden variables, these locations, and then you really would have faster than light singling, because if you knew lambda, then you could work out what the actual measurements that they had made. But with Kent's interpretation, it just seems completely impossible that anyone really could know what this hidden variable was. So I don't particularly have any hang-ups if parameter independence holds, and I really do find it rather hard to see how parameter independence could hold in Kant's theory. Another way, if you really want to cling to parameter independence, then another possibility would be to actually say that mu here is not independent of O hat here. And again, this seems you must have some kind of dependency of mu on O hat, because really this lambda here really encodes all the kind of experimental configurations that have been set up. So you wouldn't expect mu to be independent of O hat. So, and in that sense, this integral isn't, I guess it's not really well defined, because here, you know, if you sum over all these, if you consider all these different possibilities, you can have all these different kinds of measurements that are going to take place. So, you know, you could just say that Kolbeck and Renner's theorem, and those who've spoken more about it, this just really isn't at all relevant to what Kant has to say. But I mean, this is probably not, for some people, this is going to be a rather bitter pill to swallow, because they're going to be people who really want to cling to parameter independence for the series to be consistent with special relativity. So I'll just briefly conclude. So Kant's theory can probably be developed into a theory that is experimentally indistinguishable from quantum theory. So when I say that it probably can be developed, because we've only been looking at toy models, so it doesn't seem to be beyond the realms of possibility that if we had a better understanding of quantum theory, then we could and further developed Kant's theory that they could be shown to be experimentally indistinguishable. And so the jury, according to Butterfield, is still out on whether Kant's theory violates parameter independence. But personally, and it's not obvious to me that if Kant's theory did violate parameter independence, then it would contradict special relativity. Okay, thank you.